Thank you very much for this introduction. Thank you everyone to be here this morning for my PhD defense, which is entitled Experimental and Numerical Analysis of the failure modes induced in ceramic materials under dynamic loading. So all the members were introduced. So I deeply thank all the members of the jury for reviewing my work and allowing me to proceed for this defense. So first, what is the context? This is a current challenge that we want to improve the armor protections for the protections of soldier and officer. And to do that, we need to have high performance armor protection, but which are also lightweight. To do this, we use, for example, a bulletproof vest in which we can have a hard plate which is going to absorb the energy of the bullet. These plates can be made of metal, but with this type of solutions, we reach relatively high levels of weight. For example, a complete protection would be more than about 40 kilograms. So this is why we are working on other solutions made of ceramic materials to decrease this weight. The ceramic is always used in combination of a backing, but with this type of solution, the complete weight is lower than 2 kilograms. So it's at least twice lower than for a metallic protection. Now, the idea, you would think that, well, ceramic, for us, we think about something very fragile, very brittle. So how can this type of material be very resistant against a bullet? Well, yes, we have solution to make this type of material very efficient in this type of application because the ceramic plate is very hard and presents a good dynamic performance. Now, if we want to decrease this weight, we need to improve the material according to its application. To do this, we need to be able to understand the failure behavior of this type of material. However, so far, this is a big question. We don't really understand what is the behavior of this type of brittle material. For this reason, the main way to optimize this type of material is to use what we could say is a make and shot approach, where we create with different recipes a large variety of materials, and then we impact them and we see how to improve the performance. So here you have a ballistic impact on a ceramic, and you can see the high fragmentation of this ceramic. So here we need to first be able to develop tools to characterize the material, then a modeling to model the behavior, the failure behavior, to in the end be able to design this type of material. So during a ballistic impact, we have three main stages. We have the very first microsecond of about till 2 microseconds when the projectile is starting to touch the ceramic, and here we have a very local high confined compression, which is going to induce some local plasticity in the ceramic. Then we have a dwell of the projectile on the surface of the ceramic, and during this stage, the ceramic is going to undergo a very intense tensile fragmentation, and the projectile as well. And the last step, for more than about 50 microseconds, this is the stage where the projectile is going to penetrate through the debris of the fragmented ceramic, and then the backing is going to absorb the residual energy and confine all these fragments of ceramic and projectile debris. So here you have an image of a torso plate where we have a central part which is very highly fragmented, and then further from this point, some radial cracks and circumferential cracks. There are plenty of different types of ceramic presenting various microstructure which can be used for armor protection. So here you have, for example, the Xoloy SA and the Forceram material, which are a commercial product of the company Saint-Gobain. From these different materials presenting dense microstructure or mesostructures with large grains or multi-phases, we can do an impact test where we generate an intense fragmentation in the material. And what we can see is that we have a link between a difference between the type of material, its microstructure, and the resulting level of fragmentation. Then we can do a further impact on this pre-fragmented ceramic here with a perforating projectile to evaluate the residual strength of the pre-fragmented medium. By this way, we can actually, by recording the velocity of the backing at the rear face of this system, we can evaluate the residual strength of the pre-fragmented media. So here, for example, you can see these very big jumps for the material for ceram, which actually traduces the greater performance to the projectile penetration. So we have a link between the microstructural properties, the fragmentation intensity, and the resistance of the projectile to projectile penetration. This type of materials, ceramic materials, is brittle materials. This means that this type of materials are going to have certain specific behavior. So first, they're highly sensitive to the presence of pre-existing defaults. So here you have images of material presenting porosity in the microstructure, which are the main defaults. And this type of material, because they are brittle, they present a high strain rate sensitivity in their behavior. So here you have Monte Carlo simulations, which showed that the expected strength of a ceramic material, silicon carbide, is expected to change according to the stress rate level. And at high stress rates, we actually reach an improvement, an increase of this strength. This is due to the fact that according to the loading rate, we are going to induce a single fragmentation on few defects or a very intense multiple fragmentation after a certain threshold. So there are two main questions that I'm going to address in this work. The first one is how to take into account the real flow population in a model, and then how can we select and impose a controlled strain rate in dynamic experiments? So when we look at the literature, we have some experimental setup to characterize the tensile behavior of the ceramic, because here we are going only to focus on the tensile behavior, which causes the fragmentation of the ceramic. So the goal is to, with this experiment setup, to reach high strain rate, which with a controlled strain rate, and to be able to reach some quantifications such as the cracking density and the material strength. The first type of experiment are Brazilian tests or Hopkinson pressure bars, but they are very limited in terms of strain rates, level of strain rates that we can reach. To reach higher level of strain rate, we can use the plate impact configuration, which allows to reach very high strain rates. And with a spooling configuration, we can generate a tensile loading. However, in this configuration, we don't manage to reach a controlled strain rate in the material in the failure area. The next type of tests are fragmentation tests, which can be edge-on impact tests and the normal impact test. So these are two configurations that exist in the literature and provide a relatively high strain rate, which can be estimated. And if we look at the type of fragmentation that we would get from these two tests, we have the development of radial crack from the impact point. And this configuration allows to estimate the cracking density in the material. Then, in order to also quantify the strength of the material, there is the JEPI technique, which can induce a spool failure in the ceramic at a controlled loading rate in the failure area. This technique is very specific, so we induce an impulse current in electrodes, which generate a magnetic power, causing the failure in the material. However, this technique presents some main limitation. It's difficult to set up, it's very expensive. So for this reason, we are going in this PhD to develop a new technique in order to reach as well control strain rate and homogeneous in the failure area. So these in yellow are the two configurations, type of configuration that I'm going to present today. When we look at the modeling part now in the literature, well, we have several models, but in our case, for brittle materials, we want to take into account the material microstructure and its sensitivity to the loading rates. So the most commonly used model to model a ballistic impact is the Johnson-Holmquist model, which is a plasticity model on which we impose a criteria of hydrostatic pressure. Even though it is very highly used, this model for confined compression and tensile behavior, there is no sensitivity of the tensile strength to the strain rate, and there is no consideration of the microstructural defects. For this reason, because we want to implement the microstructural defects, we are going to focus on micromechanical models. One possibility is to use the DFH model coming from Denouin-Fourquin-Hild, which is a micromechanical model which can be used to model the tensile damage behavior in ceramic materials, in brittle materials. Here in this material, we take into account a random distribution of flows in the material. When we apply a tensile loading, we are going to increase the stress in the material, and when it's overcoming the failure stress of one defect, some cracks are going to trigger from these defects, and these cracks are going to induce a release of stress local, which can be represented by this obscuration zone, and any other pore or defect in this obscuration volume cannot be triggered anymore because of this drop of stress locally. Very good point of this model are that it can predict the sensitivity of the tensile behavior according to the loading rate. The output of the model can be compared to some experimental data. And most of all, there is an implementation of an explicit density of the critical flow population in the material. However, this last point might present some few limitations that we will go deeper in this presentation a bit later. So here you have the methodology to, in the end, develop a new experimental and new modeling methodology to study the loading rate effects on the tensile dynamic behavior of ceramic material. So first, the methodology is to start from several materials that we are going to characterize, then to perform some dynamic tests on these materials. In parallel, develop a methodology for the modeling based on X-ray tomography analysis. And by combining all of this, the idea is to see if we manage to improve the predictions of the DFH model compared to the experimental results. So first, for the microstructure part. In this work, I'm going to present the results for two materials, which are two dense silicon carbide made from solid-state pressureless sintering. So the first one is the material called Exoloy SA, which is a commercial armor product of the company Saint-Gobain. And this material presents a low amount of porosity. Here you have some SEM images at different scales showing these porosity, sintering pores at the boundary of the defects. And the second material is a derivation of this material where we have about the same microstructure, but there are some very large and spherical pores in this material. For this reason, we are going to call this material Exoloi SACP, CP for size-controlled porosity. These pores represent about 2% in volume. Now, we've done some tomography analysis on these two materials. So here you have some images of the post-processing of tomography 3D images, where we extract from a grade level thresholding only the porosity, which are the main defects present in this type of material. To reach these different defects, we have to reach high spatial resolution for the tomography scan. So we have very small samples to be analyzed from tomography. Then, from this extraction of pores, we can analyze the distribution of the defects, their size, and we can obtain this distribution, this plot, where we have the cumulative density of flow in the material according to the equivalent diameter of a defect, which is taken equal to the equivalent diameter of a sphere of the same volume. Here you can see that we've done tests on different resolutions in the scans. So we've done several scans at several different resolutions to be able to capture a large range of the different defects in the material and be able to represent properly the defect population. What you can say is that first, the material Exoloi SA seems to have a slightly lower amount of small pores compared to the other one. And the Exoloi SACP present this very large plateau, which actually traduces the fact that it's in this material, we don't have any pore, almost any pore, in between 15 to 40 micrometers of equivalent diameter. So if we focus on this Exoloi SACP, we can see that we have different types of pores. We have the very small ones, which mainly are sintering defects. And when we look at the sphericity factor of these defects, we can see that they're not very spherical. So we have a big cloud here. When we reach a sphericity of 1, it is a perfect sphere. For larger pores, we can see that we have pores which are extremely spherical and reach a sphericity of about 1. And then we have a last population, which is a bit less spherical, which actually corresponds to these large spherical pores, but which are touching. So they are merging, creating something a bit less spherical. Now on these two materials, we've done some dynamic tests. First, we've performed fragmentation tests which are the edge on impact test. And here you have elastic simulation showing the fields of stress propagating upon impact in the material in the radial stress and hoop stress. You can see that the impact is generated a compressive loading in dark here, which is inducing a tensile loading in the hoop stress along the axis, the loading axis. So here we managed to generate tensile loading in this configuration. The second type of impact that we've done is normal impact. So here you have a quarter of the system, and we are looking at the rear face of the ceramic. And we can see that in this configuration, we managed to induce a tensile loading, a tensile failure, well, tensile loading at the rear face of the ceramic. So this is in this position that we are going to study the output data. So in these two configurations, one idea is to be able to quantify or evaluate at least the strain rate level reached in specific areas in this configuration. So first, for the edge on impact test, we use two points along the loading axis. And in this point, we've plotted the hoop stress evolution with the time. And here you see the plots, and from the slope of the tensile loading, we can actually have a numerical evaluation of the stress rate level in this material, in these positions. For the normal impact, we did absolutely the same, but we've taken some points at the rear face of the ceramic at 7, 10, and 30 millimeters from the impact loading direction. So from this, we can evaluate the level of strain rate reached at given position in the ceramic, and we are in between 10 to the power 2, 10 to the power 4 per second for the two configuration, and we have an overlap, which is going to be interesting for comparison. Then we've performed the dynamic test. So here you have images for the edge on impact test, where you have a scheme, a top view of the configuration. We've used a marble polished surface for the ceramic to be able to visualize the fragmentation in the tile upon impact. For this, we are using an ultra high-speed camera with a frame rate of about 5 million frames per second, and we are using a flashlight because the event is going to be extremely quick. The fragmentation that we are going to see developing in the upon impact here in the two material is about after 4 microseconds, the ceramic is fully fragmented. So you can see here some radial cracks nucleating in the ceramic, and then some hoop cracks in a second time generated in the tile. Now, the idea is to be able to quantify properly this cracking density. To do this, to be able to quantify in a specific location in the tile, in the post-mortem sample, we had to keep all the fragments in position upon impact. For the edge on impact test, for this, we use a sarcophagus configuration with a transparent polycarbonate sarcophagus. And for the normal impact, we used a metallic sarcophagus, but after the impact, we've infiltrated the fragments to keep all the fragments in one single piece. And these two post-mortem samples could be observed through X-ray tomography analysis. So here you have some images of, well, a 3D volume of the post-mortem sample captures from X-ray tomography, which was post-processed so that we could identify the cracks and individualize the different fragments. So here we have a view where we are going through the sample for the two configurations. Then for the quantification of the crack density, we took the exact same position where we had the estimation of the strain rate from numerical simulations. And we count the number of cracks that we obtain experimentally close to these positions. So for the normal impact, we are just looking at the rear face of the ceramic where we generate this tensile loading. So by this way, we can have different positions where we have an estimation of the strain rate, and we have here a quantification of the cracking density. Here you have a plot where we compare for the two materials the evolution of the cracking density according to the strain rate evaluated numerically. First, we can see that for both materials, we have a sensitivity, but for the material Exolite SA, we have a higher sensitivity. And what is very interesting is that we have a threshold in between. We have an inversion of the behavior of the intensity of fragmentation for both materials. So the Exolite SA material presented a lower fragmentation intensity at low strain rate, but once we go above this threshold, it presents a higher level of cracking. If we add some few points for the Exolite SA in the edge on impact configuration, we can see that the results are pretty close between the normal impact and the edge on impact results. So here we have a quantification of the cracking sensitivity, cracking density sensitivity to the loading rate. Now we want to also be able to quantify the strength of the material under tensile loading. To do this, we need to have an experimental configuration which can generate a control tensile loading in the ceramic. So for this, to have access to a high strain rate, we use a plate impact configuration. So basically, the plate impact test, we have a fly plate, which is going to be the projectile, let's say, the target, and we are going to launch this fly plate, and the contact with the target is going to generate compressive waves, which are generated here in both materials in opposite direction, and they're going to be reflected at the free surface of both material, and the overlap of the two release waves is going to generate a tensile loading in the material, which can cause the failure in the spool failure in the material. In the classical configuration, there is one main limitation, is that this flat contact is going to generate a compressive wave which has a rectangular shape, because we have a jump of stress upon impact due to this flat contact. The idea here is to be able to control the loading rate during this test. To do this, we need to avoid this rectangular shape for the compressive pulse. So to avoid this stress jump during the overlap of the incident wave and release wave, we can actually shape the compressive wave into a triangular pulse. And by this way, when the triangle pulse is going to be sent and then reflected, the overlap is going to generate an homogeneous loading rate in the failure zone of the material. And we can see that we have this plateau of the superposition of the two waves, which is leading to a constant levy of strain rate. So now, how do we get this triangular pulse? So to do this, we did some numerical simulations where we decided to pattern the front face of the flyer plate. We've patterned it having some wavy shapes. These wavy shapes aims at changing the shape of this compressive wave. So here you have numerical simulations where in the end, we used a 2D model to be able to design the front face of the flyer plate. We've tried different geometry. So here you have 4 of them playing on this, the height of the pattern, and it's so it's a cosinus shape, and we are playing on the height and the period. We've optimized numerically the shape of this fly plate, playing on the material properties, on the shape of the profile. So here you have numerical results where we have a difference of the shape of this triangular pulse for different impactor geometry of fly plate. And we also play on the impact velocity, which also has an impact on the shape of this triangular pulse. We've selected the best configuration where we could have a pretty good triangular pulse from the numerical simulations. So here you have the several reference configuration that we are using for the experimental test. So we have 4 different flyer plate geometry at different velocity. So now we've designed this fly plate to reach a triangular pulse. Now let's see for the experiments. So the experiments are done with the gas gauge at 3SR laboratory. So we perform plate impact using this launcher, where we actually put the projectile in here, and it is going to be launched in this long tube, and it is going to impact the ceramic target in this big chamber, which is put under vacuum. So here you have images of the projectile put into a sabot and the target. on which we actually have put a buffer plate, which is just a mechanical filter, which is going to transfer more homogeneous loading to the ceramic. Then we had to make sure that during the test, we don't have any tilt between the fly plate and the ceramic. So we had to work on some alignment systems. We had to make sure that we control the impact velocity of the during the test. And in the end, we want to capture some data from this experiment. So to do this, we use interferometry systems where we actually put two optical fibers at the rear face of the ceramic to capture some data. We'll see that later. So we had a lot of setup to work on to be able to do this test. I would say it took about 6 months to design the projectile and be able to understand how to make the test and get something out of it. Well, a test is about 1-2 days. And in the end, the result is just, well, 3 microseconds. So you can imagine the different scales of time. But we need to capture everything from these 3 microseconds. So this is why putting all the trigger and things like this are very important. So here you have a scheme of the setup where you have the fly plate, the buffer, and the ceramic. We've decided to translate slightly the ceramic according to the loading direction to be able to actually use a first laser interferometer at the backing, at the rear face of the buffer plate. By using this laser and some post-processing, we are able to evaluate the buffer free velocity. This information can be converted into a transmitted stress, which is going to be transmitted to the ceramic. And you can see here for all the different configurations that we've used that we managed to reach a triangle pulse. So we see that it is working. We can also, by playing on the different shapes and configurations, we can change the shape of this, transferred stress. Then we've used this experimental pulse as an input for numerical simulations to evaluate what was the strain rate generated upon impact in the failure zone. To do this, we've done numerical simulation, elastoplastic simulations, and this allowed to evaluate the strain rate. In parallel, during the test, we use a second laser interferometer, which is capturing the free velocity at the rear face of the ceramic. Here you have the obtained profile for the free velocity, where we can see that we have a ramp loading, and then we have a drop of velocity. This is traducing the failure of the material under the tensile loading. The gap of velocity here, the drop, is called the pullback velocity, and it can be used to evaluate, to measure the spall strength of the material using the numerical formula. From all these results, we can get to this plot where each point is just one single experiment. So here you have for the material Xaloy SA, the evolution of the dynamic strength according to the strain rate. You can see that we have a sensitivity to the strain rate. We can also see that for 2 tests in the exact same configuration, we get the same results. So good reproducibility. We've compared these results on experimental results obtained from the JP technique that are present in the literature on the exact same material. And we can see here that we have a good fit. We have something which is coherent between the 2 techniques. And we've done some additional tests on the Xaloy SACP, and we can see here that the dynamic strength, tensile strength, is slightly lower than the first material, but still we have this sensitivity to the strain rate. So now that we have experimental data, in parallel, we're working on a modeling work to be able to predict the behavior of the material. So the current DFH model is actually using a specific specific data to describe the critical density of defects. Currently, what is used is that we use the DFH model, the Veblen model, sorry, which says that we have a probability of failure in the material, which is related to the flow population that you have right here. And this flow population in this Veblen model is expressed according to the principal stress, sigma, and the Veblen modulus, m. In order to get and reach this m parameter, we need to do quasi-static bending test. So here we can evaluate this parameter m from the scattering of the results obtained from bending test. What we can see is that the parameters that we are going to obtain from this bending test highly depends on the effective volume that was loaded during the test and the most critical defect that is into this loaded volume. However, if we zoom in, for example, this material, we can see that we have all the defects, which are here porosity, but are way smaller. And these defects are not going to be triggered during a quasi-static bending test. So the big question is, do we actually need to characterize these defects and implement them in the model to have a good characterization of the behavior of the material? In order to reach a complete description of the flow population, what we did is that we used X-ray tomography. So here you have the classical approach with the Veblen law obtained from quasi-static bending test, and the Veblen modulus is the slope. The question is, how can we use the tomography data to have this plot of the cumulative flow density according to the critical stress? To do this, we can use the linear elastic fracture mechanic, where we express the critical stress of activation of a defect according to its size. Here we have this Y parameter, which translates the shape of the crack, the Y parameter, which translates the shape of the crack. This parameter needs to be calibrated. To do this, we actually plot the conversion of the plot, but for different values of Y, and the best value is the one fitting the data from bending test at the level of the average bending strength. One hypothesis that we make here is that we have a constant parameter Y for all the defect populations. So here we have a parameter of about 0.85. And from this curve, we can now fit a continuous function that we can get explicitly and that we will use and implement in the model. So we did the same for the material Xolay SA. Now, here we have the input of the DFH model. So it's for both materials, the distribution of critical flow that we've just obtained. We can see that for the Veblen material, for the Xolay SA material, we have almost the same thing between the Veblen approach and the continuous approach. So when we are going to apply the DFH model and the analytical formula to get the strength, we have almost the same results. However, for the second material, the large difference in the critical population of defect is going to lead to a big difference in the strength sensitivity to the loading rate. And you can see here that at high strain rates, we actually have a very high increase of the strength of the material, which is not captured in the Veblen approach, from the Veblen approach. Now, if we do the same to have the predictions of the DFH model, but for the cracking density, well, we apply this analytical formula with the evolution of the cracks in the material, and we can get the evolution of the cracking density according to the strain rate. What we can see for the Xolay SA, it's pretty the same due to the same input data. And for the Exolite SACP, we can see that we have a plateau which leads to a lower cracking density than what would be expected from the Weibull approach. In order to understand better this phenomenon, we've developed another approach based on X-ray tomography, but which is a discrete approach in which we capture the defects during the tomography scan at the exact same position and with their size. And from this, we create a numerical volume on which we are going to do tensile loading at a given strain rate. And at a given strain rate, we can actually identify which were the pores which were triggered in the configuration. So here you have an histogram where for a given strain rate, you have the population of defect that was triggered. So at low strain rate, what happens is that we only trigger the largest pores. When we increase the strain rate, we reach this plateau in the input function. So this is why we are actually also reaching a plateau for the cracking density. So here we limit the increase of the cracking density thanks to this plateau. And well, at higher strain rates, we start to capture the very small sintering defects. So this is why the cracking density is increasing again. So here you have some few images of a discrete simulation where you have the obscuration zones growing from the triggered cracks. At low strain rate, it's just few defects, and at high strain rate, you have a high amount. So now from this data, we've done some comparison between the experimental test and the modeling. So in the DFH model, before in the simulation, here were the input data. Now we've changed that. We've deleted the Weibull parameters, and we've used our continuous function that we can explicitly implement in the model so that we can run numerical simulations with this DFH model using a realistic distribution of flow in the material. From this, we can have a mapping of the cracking density, which can be compared to the cracking density which was obtained experimentally, for example, here for a normal impact. When we compare the modeling and the experimental results, we can see that we are in a pretty good range compared to the modeling. However, we can see that at high strain rate, we tend to numerically underestimate slightly the level of cracks. One hypothesis is that in this high rate level, so close to the impact point, the density of cracks is very intense. So with the spatial resolution of the tomography, we are limited to capture these cracks. Now, when we compare the results of the shockless plate impact with the prediction, we can see that for both materials, we have an extremely good prediction with the DFH model. We can see that we have a good fit with the experimental data, and still here we know that we would need to perform some more experiments at higher strain rate to be able to demonstrate experimentally that using flow distribution based on tomography data, capturing the smallest flow would be required to have a proper description of the material. When we compare the two materials, we can see that in the end, the very high increase of strength sensitivity above a certain threshold for the Exolite SACP leads to, in the end, reach higher level of strength compared to the other material which did not have these large spherical pores. So in the end, here are the main conclusions of my PhD. So we needed to have a new methodology in order to first study the strain rate sensitivity of the tensile behavior and then evaluate the role of the flow population. To do this, we've developed new experimental technique combining fragmentation tests and tomography post-processing. And we also developed a very original technique based on shockless plate impact. We've improved the modeling using X-ray tomography to properly characterize the full distribution of the defects. We've developed a continuous and discrete approach to understand better what is the role of the defects. And we were able to implement this continuous description into numerical codes to predict the fragmentation of the material. There are main perspectives for this work. So first, for the experimental part, we would need to try to reach higher strain rates. So to do this, we could use the shockless plate impact, but in samples in a sarcophagus configuration, and design new flyer plates to reach higher level of strain rate. For the modeling part, now that we've seen that we can have an explicit continuous description of the flow population, we can now play on the shape of this continuous flow that we can decide and see what is from the DFH model, the output, and how to improve the strength of the material by this way. We can also extend this approach to other types of material. Here we are on, let's say, ideal microstructure with pores, our main defect, but we could extend by some adaptation this approach to material presenting a mesostructure where the size of the grains is going to have an influence, or the different phases is also going to have an impact on the behavior, failure behavior. In the end, the main goal is to reach a numerical simulation which is realistic compared to ballistic impact. And we saw that the ballistic impact is divided into three main steps. So here we need to find, to extend this work to have a robust modeling of the compressive behavior under confined compression. Well, for the tensile behavior, this is what we did today. And for the behavior of the fragmented ceramic. So thank you very much for your attention. I want to deeply thank all the people who helped me for the technical support, for the tomography analysis, for the plate impact, and all the other experimental work that I did. And I also want to deeply thank the organizations involved in this project, so the Université Grenoble Alpes, the company Saint-Gobain, which provided all the samples, and the DGA. Thank you very much.